Dun, 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 dun. Dun, 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 dun. Insert the music here. Insert the music here. All right. Good evening and welcome to Merriwether's World. I am your host, Dr. Mark Merriwether Vorderbruggen, creator of Foraging Texas, author of Idiot's Guide Foraging, medicine man at Medicine Man Plant Co., and all around way too busy for my own good. So tonight, it's a very, very, very special episode of Merriwether's World. I am very, very excited about this. And so excited that we're going to make some changes. So I'm going to start with a brief little housekeeping type stuff. But to make sure I can squeeze in all the information I want to get to tonight, I'm moving all the sponsors to the end. So, yeah, you won't have to put up with that. And for my sponsors, sorry, but this is important. So, like I said, I am the host, Dr. Mark Merriwether Vorderbruggen, creator of Foraging Texas. I'm just putting a link up here to the Foraging Texas website and a few other things, my book, YouTube channel, things like that, where you can see all the upcoming classes. Right now, the main upcoming classes, this weekend I'll be at Jesse H. Jones, but you need a reservation for that. It's, last I heard, they're all booked up. December 5th, I will be up at Dallas teaching for Texas Survival School. And then December 19th, I will be in Austin. Let's see. I don't care about ads. Okay, yeah. December 19th, I will be out on the west side of Austin at Spoke Hollow Outfitters. And after that, it pretty much jumps into February. So we got that going for us. All right. So, sorry, I got sausage stuck in my teeth. Also, because of the amount of information I'm trying to get through tonight, probably not going to do the usual shout outs to people. I will be looking for questions, so I will try and answer questions that pop in, because you'll probably have questions, and I'll do my best to answer them. But like I said, tonight, I'm trying to explain to you the universe. So it's going to take some doing. And let me silence my phone. All right. So, like I said, this has been coming for a while. This actually, I love connecting people to nature and plants in general. And I mean, the chemistry, the fascinating, the growing, the ecology, the relationships, all that sort of stuff absolutely fascinates me. And anyone who takes my classes knows how passionate I am about this sort of stuff. But honestly, it goes deeper, and just trying to really understand the universe itself. And so this has been coming together for a while because it seems kind of important, because a lot of people, they have some vague ideas and stuff, and vague ideas don't capture, for lack of a better term, the miracle of the universe, the amazing, everything that went into it. And so to try and talk about the universe, I decided, well, what is the most boring, simple thing? And let's trace that back. And so after thinking a bit, a grain of sand. Simple grain of sand. The universe is filled with uncountable grains of sand. Behind me is Spring Creek, the creek that runs between Harris and Montgomery County. That's my normal stomping grounds. And so let's picture a grain of sand picked up from the creek here. So we got a grain of sand. We're looking, okay, it's mostly silicon dioxide, silicone and oxygen. There might be some feldspar, some other minerals in there. but mainly silicon dioxide. So looking at the sand, where did the sand come from? Well, the sand along Spring Creek, it's mainly released from sandstone deposits. So way back somewhere, you might have heard of the three types of rocks: the sedimentary, the igneous, and the metamorphic. The sand from Spring Creek, it comes off sandstone. So basically sandstone, it's grains of sand glued together with some other material, usually calcium carbonate, or just a lot of pressure. Okay, good. So we got grains of sand that are being released from sandstone. Okay. Next question. Where is the sandstone from? Good question. I'm glad you asked that question. So, like I said, the sandstone is considered a sedimentary rock. So the sandstone is the result of lots and lots and lots of sand a long time ago, coming down from a mountain in a river, washing into an ocean or a sea. And over the course of many, 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 many years, piling up on top of each other more and more until the very weight of it forces it down, heats it up, and starts to glue it together. So the, let me just check here. Yeah, so the sediment that formed the sandstone in Spring Creek is estimated to be about 488 million years ago. So 488 million years ago, sand came down off a mountain, rolling around, tumbling around, ended up in an ocean that was here. If you go back then, because of plate tectonics and all this stuff, very different ocean, the sand ended up in the ocean. More sand, silt, clay, algae, clamshells, all this stuff, ends up there, presses down, forms sandstone. Pretty cool. So the sandstone is sitting there. All this stuff, lends up on top of it. It gets buried. So the sandstone can be, a mile deep. But then through the action of the ocean and rivers and all this stuff, eventually the sandstone gets exposed and starts releasing the sand into Spring Creek. Okay, makes sense. So it came off a mountain. What did I say? 488 million years ago, there were some mountains around that released the sandstone into, or the grains of sand into the streams running down the mountain, washing it into what became the sandstone for Spring Creek. So to do that, most likely it was from chunks of quartz, silicon dioxide, just chunks of quartz. Quartz, it's, if you look at what's called the Mohs hardness scale, when they're measuring how hard different minerals are. So talc is really soft. You can scratch a talc rock or a chalk rock with your fingernail. Diamond is the hardest. That's like at a 10, I believe, if I remember correctly, of the hardness scale. It's super, 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 super hard. Of the naturally occurring minerals, so diamond is the hardest. Just below it is quartz. And basically, quartz will scratch everything below it, and diamond will scratch quartz, but really nothing else will until you start making cubic zirconiums and so forth. But that's outside. That's lab stuff. That's not nature. That's humans, which is pretty amazing in its right. So you got these chunks of quartz, which are, except for diamonds, some of the hardest naturally occurring stuff on the planet. And it's breaking down. Just through the action of water, cold, frost. You get cracks in it. When it forms, it'll cracks. Water gets into those cracks. That freezes way up in the mountain. And, the quartz over time flakes the little bits off. And these little bits sit, there in the soil for, a million years or so. as wind and gravity and stuff causes them to bang against each other and slowly break off these individual smaller grains to the point where then some water can come through and wash it into the creek, and then spend maybe another million years getting it down to the sediment. But just the action of water and cold is enough to break this quartz into small pieces. Let's go sideways for a second. Let's talk about mountains. Let's talk about the age of mountains. So right now, tallest mountains in the world are the Himalayas. They're also considered pretty much the newest mountains in the world. Remember, mountains come from two tectonic plates smashing against each other and pushing upwards. So the Himalayas are due to India colliding with Asia and forcing the mountains up. So the Himalayas, and let me check my notes here. Where do I have my Himalayan notes? Okay, yeah. So the Himalayan mountains are only 50 million years old, 50 million years old. So the sandstone that ended up being Spring Creek, that was laid down well before the Himalayas ever started growing. So let's say you grow some big mountains, and then over time, the cold, the water starts breaking the mountain down. How long does that take? Well, if you look around the Earth and you look at different ex-mountainous areas, so like Appalachia, we'll stay in the US for now. So Appalachia, the Black Hills, two different places. So like the Black Hills are mainly in South Dakota. Appalachia kind of runs up through the eastern side of the US. So, or even the Rocky Mountains. Rocky Mountains are pretty big and jagged. The Rocky Mountains are slightly older than the Himalayan mountains. So the Rockies are between 55 and 80 million years old. So they're still big and tall and jagged and impressive and hard to get around and everything. So they're old, older than the Himalayans. But let's talk about the Appalachians. People have a vague idea, the Blue Ridge Mountains, kind of these rolling hills. 1.2 billion years old. So if it took them, let's say 50 million years to grow up to big, Himalayan style peaks, it then took 1.2 billion years to wear them back down into rolling hills. They say a person really can't grasp more time than basically back to their grandparents. So let's be generous and say 80 years. Beyond that, they can't grasp it. So trying to grasp the difference between 50 million years and 1.2 billion years, the brain can't grasp that. It's just a long damn time to break those mountains down. The Black Hills in South Dakota, they figure those have been around for 1.8 billion years. 1.8 billion years. There's actually they are some of the oldest mountains still remaining on the planet. So it takes a long time to wear down a mountain. That's pretty cool. But it happens because nature goes at it slowly, bit by bit. Like I said, the quartz, water gets in there, freezes, spalls. The flakes fall down on the ground, and over a long time, wind and shuffling and snow melt and all that bangs them together. Once they get into a stream of water, the tumbling starts breaking them down more. But yeah, we're talking billions of years. So the sand back here in Spring Creek, came from a mountain, probably, let's say 1 billion years ago. This is when the mountains first formed. Actually, probably longer because, you look around, there aren't really any mountains around, but a long damn time. So then the question is, well, okay, we already talked, mountains are formed when you got the two tectonic plates smashing against each other and thrusting up. And to grow some decent sized mountains, it takes about 50 million years. So we got chunks of quartz on the mountain. Where do those chunks of quartz come from? Well, they came from, the magna layer. Because remember, I'm trying to think how to do this. Oh wait, this probably won't work. But imagine this green piece of paper is the magma, and then my fingers are, just the upper surface of the earth. So as it gets thrust up, you get this magna layer in the heart of the mountains, and so you get volcanoes. But that magna layer, that's the molten rock. Now, if you look at the earth, silicon makes up 28% of the earth. That's a lot. So the magma is very, very silicon rich. So it's coming up. So you got this silicon dioxide, molten. It's not molten silicone. It's molten silica dioxide. So melted quartz, melted glass, really. And it's being thrust up in these mountains. A lot of times, there may be some volcanic activity, things like that going on. But volcanoes are another good source. But you have this particle. Think of it. Let's just talk now about one molecule of silicon dioxide that's come up from the magma, from somewhere in the molten part of the planet and up into this mountain, and then hung out there for 1.2, 1.5 billion years until it finally, got washed into the water. So this silicon, the single silicon molecule, silicon dioxide molecule, came up as the mountains grew. That probably wasn't the first time that silicon dioxide molecule was involved in a mountain, decayed down the mountain, got washed into some water, got washed down into an ocean, and formed a sedimentary rock down there. The scientists are figuring it on most of the silicon dioxide. It probably happened about 4 times. So when you get washed into the ocean, so if you have let's go this way. If you have 2 plates on the earth smashing together to grow the mountains, other places on the earth, either you have plates pulling apart, like the Great Rift Valley in Africa. That's actually 2 continental plates pulling apart, making this really bizarre valley. But another thing that's going on is usually out in the ocean, instead of them coming together and pushing like this, somehow one popped up on top of the other. And so one is going underneath it. And so instead of getting mountains, you just get a little bit of raise, but the other is going down. It's called a subduction zone. And so if this is the bottom of the ocean where there's, all the sediment and dead whales and so forth, it's ending up going down under the other plate and melting and joining the magma. A number of years ago, there was an artist that took some big granite blocks, carved his name into it, and dropped them in various parts of the ocean, thinking that they would last, forever, basically. Until scientists pointed out, well, pretty much the bottom of the ocean, all over the world, eventually what is considered the bottom of the ocean is going to end up plunging down under another continental plate and melt. And so your big rocks with your name carved in them, they're just going to melt into magma. But then eventually they may get raised up as a mountain. The mountain decays, the sand flows down, forms sandstone. The sandstone decays, forms the sand on the beach behind me. Is this making sense? Are you following? So, I mean, in the course of the Earth, they figure on average, because this whole mountain building and breaking down happens, a number of times, that approximately 4 times, depending on the mountains and locations and so forth. Also remember, earlier in the Earth, things were a lot more dynamic and corrosive, and just the process was occurring more quickly back then. Okay, so you have this silicone molecule that's on its 4th ride up a mountain, down into the water, onto the beach. Cool. It did it 4 times, most likely. That's awesome. So the question, though, is, where did it come from? And to that, we have to talk about the creation of the Earth, don't we? Okay. If I met you earlier in life, I could have just skipped school. I actually hear that a lot. Okay. So we've talked about the creation of mountains. We've talked about, the subduction and all that. We've talked about silicon dioxide and it doing its things. But let's go back farther. Like I said, the creation of the Earth. And to talk about the creation of the Earth, we need to talk about the creation of the solar system. So let's talk about the creation of the solar system. So in the vastness of the Milky Way, there are clouds of dust. And by dust, we mean everything from everything from hydrogen, maybe a little helium, but a lot of hydrogen, and then a lot of other things, mainly like iron and silicone and magnesium, carbon, oxygen. These things are just kind of in a big amorphous cloud floating around. And for the most part, they're just sitting there. Now, the force of gravity is working on it, because remember, gravity draws things together. But gravity is a surprisingly weak force. Now, I'm going to have to throw some math at you here. So let's just talk about gravity for a second. The strength of gravity reduces or decreases exponentially as you move apart. What this means is you don't have to go very far apart before the gravitational pull between 2 objects fades to almost 0. Put it in perspective. You're on the surface of the Earth. We have a gravity of 1. We'll just say a gravity of 1. To go up high enough away from the Earth so that the gravitational pull is now 0.001? No, sorry, 0.01. 1%. Yeah, 0.01. So you went from 1 to a gravity of 0.01, which is pretty much weightless at that point. You only have to go up about 24 miles. 24 miles. You just have to go up 24 miles off the surface of the Earth and you become weightless. Now, jet planes fly around 5 miles high, somewhere there. The International Space Station is at 220 miles above the Earth, but you only have to go up 24 miles to where this huge mass of Earth really no longer has any pull on you. Now, you only have to go 24 miles away from the Earth for it to really have very minimal effects on you. Imagine now particles of sand and particles of dust, or even just hydrogen. Very, very, very little weight. So they are drifting around and not really interacting with you. You just got this fog of stuff, almost invisible. And so that's going on. But then somewhere more than 4.8 billion years ago, a shock wave came through this cloud of dust. And this shock wave shoved things together, and it deposited particles, And we'll talk about where the shock wave came from, but it deposited stuff in there. And so suddenly you got this compression wave going through this cloud of dust. And it actually forces the things together close enough that they can start interacting with each other's gravitation. You know, they're close enough now where they can start collecting through gravitation. And as the particles come together and form bigger clumps, their gravitational pull increases. So suddenly you have this thing where these particles which were floating away are suddenly kind of jammed together. And because they are jammed together, they start attracting other atoms and molecules floating around them. And so this big mass starts just swirling around itself. And kind of, if you've ever run a centrifuge and you take, let's say, a beetle or maybe several beetles and run them in what's called an ultracentrifuge, where you spin it around so fast that the beetles break apart into their individual components, with the most dense at the outer and lighter in, and you basically separate the things by density. Well, that's kind of what's going on, but not only it's not as fast as an ultracentrifuge, it's more of a speed thing and how things are reacting to the gravity. Okay, so you have this mass swirling around. Now it's mainly hydrogen. So the hydrogen is going to form, you know, the most of it, but you have these other elements, like I said, the carbon, the oxygen, the iron, the gold, uranium, you know, basically, you know, these sort of guys ignoring a lot of the transition. But you got these elements swirling around, and eventually they start forming, you know, rocky bits, proto chunks of planets and so forth. But at the center, where it's swirling the fastest and pulling together and things are clumping together the most, you got a lot of a lot of hydrogen there. And normally you can only get, you know, things too close. Like if you press your hands together, no matter how hard you can press really hard, they're not going to join. And, you know, you can press things, you know, put things in a vise and crank on it. They're only going to get so close together. And if we have time, we'll talk about what's going on there. But with hydrogen, you can only get two hydrogens so close together. They just won't go any closer unless you really, 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 really increase the pressure. So as the gravitational pull is working on it, you're getting this huge mass of hydrogen being pushed tighter and tighter and tighter together. Suddenly, they overcome their natural resistance and they fuse together. And so two hydrogen, a hydrogen has just one proton, no neutrons, one electron. They fuse together and form a new atom, helium. Helium has two protons, two electrons. So fusion, you might have heard the term fusion. In the sun, it's fusing. So the gravitational attraction of such a large mass is enough that at its core, the pressure is enough to fuse together two hydrogens into one helium. Now, somewhere along the line, you may have heard the Einstein's equation, E equals mc squared. So energy is interchangeable with mass times the squared speed of light, the universal constant in the speed of light. So when those two hydrogens are fused together, if you weighed them, if you weighed the two individual hydrogens and the resulting helium, you would find there's a very, very small difference in the weights. The helium weighs just a little bit less than the two individual hydrogens. So what happened to that mass? Because you think mass can't be destroyed or created in the universe, it's a constant. Well, mass energy can't be destroyed. So that missing mass, that teensy little bit of mass difference between two hydrogens and one helium has been converted to energy using the equation energy, E equals mc squared. Following me? So that in this case, the M, the mass, is that little tiny bit of difference in weight between the two hydrogens and the one helium. And so that energy that's released, that nuclear explosion, is so vigorous that that's what we see as the sun. It is the mass being converted into energy by that E equals mc squared as the hydrogens fuse into helium. Now, the energy released is such that it kind of pushes outwards. If you take a balloon and start hitting it with a hairdryer, heating it up, the balloon expands. So as you know, once that hydrogen ignites, once that fusion starts, so it was, the star matter was tightly packed by the gravitational pull. But then it expanded a little because of the heat, but it didn't expand so much that the fusion stopped. So the hydrogen is still close together enough where it's starting to fuse into the helium. But the overall size of the star has expanded some because of the heat, the energy being produced. Okay, let me take a sip here. Okay, so you got hydrogen burning, forming helium. It's expanding the star. And that's what our sun is doing right now. So our sun was a cloud of hydrogen that got compressed somehow and started swirling around and got close enough, and gravitational pull pulled enough of it together for the fusion to start. Meanwhile, around it, we got the rocky planets. We got Mercury, we got Venus, we got Earth, we got Mars, we got the asteroid belt. And after that, you get the gas giants, the Jupiter and Saturn, Uranus, Neptune, and then you end up with a little rock again. So, the sun was mainly the hydrogen. The planets, the rocky planets, were mainly the heavy, dense matter, the iron, the nickel, the magnesium, the copper, the gold, uranium, all these sort of things. The silicon, the oxygen. Like I said, the silica is 28% of the Earth's surface. So there's a lot of silicon here. Oxygen makes up 46% of the crust. We got a lot of oxygen here. So while these, and they were generally molten when they first formed because of the friction and everything grinding against each other, you got these molten blobs circling the sun. And then eventually these molten blobs, we got the planets now, they're circling the sun. They do start to cool. So at first, that's why the core of Earth is molten, is because it started out as this molten blob of silicon and oxygen and iron and copper and all this sort of stuff. But then the crust started cooling off, started solidifying. Underneath is still liquid, and you got gravity and all this stuff going on. And so the crust is breaking and parts are, smashing together and making mountains, and others are going underneath in subduction and all this sort of thing. But you got these molten planets formed, and they're cooling and forming the Earth. Cool. So this big cloud of dust and hydrogen formed the solar system because this shock wave came through and compressed them. So, okay. But where did all these elements come from that formed all this? And where did the shock wave come from? So for that, we have to go back farther, don't we? Because they came from somewhere. And some people think, well, the Big Bang made all this stuff. Well, no. The Big Bang, and we'll talk about that, we'll get back there, but the Big Bang mainly made hydrogen. And it took a long time to go from the Big Bang to get to hydrogen. Actually, let's just jump down to the Big Bang now. So these elements came from somewhere. So let's talk about the beginning of the universe. Simple enough concept. How did the universe begin? We can cover that. So before the Big Bang, scientists have no clue. We can basically, through calculations and modeling, get right up to femtoseconds, like a 12 quadrillionth of a second after the Big Bang. But at some point, the Big Bang occurred, and what it was just this sudden release of all these particles and energy, not electrons and neutrons and protons. We're talking the fundamental, the quarks, the neutrinos, the mesons, the leptons, the things that come together eventually and form the electrons, the protons, the neutrons, which then eventually come together and form the atoms, which then come together and form molecules. But at the very, very, very beginning, at the Big Bang, it was just energy and fundamental particles in this huge, hot, expanding sphere of just intense energy. Temperature unmeasurable, bazillions of degrees heat. So hot that the electrons couldn't form. The electrons would just fly apart into their fundamental parts. The protons, the neutrons, all these things were just, everything was moving around too fast that they couldn't even come together to form electrons and protons and neutrons. So you got these fundamental particles flying all over. And I got to check my notes here, because I want to get this right. Okay, and so scientists estimate that the Big Bang happened about 13.77 billion years ago. So 13.77 billion years ago, there was this plasma fog, superheated plasma fog of fundamental particles zipping around. It was too hot for anything that we would recognize as an atom, or even as an electron, or a proton, or a neutron. But this cloud cooled relatively quickly. It was expanding at the speed of light, or maybe just underneath it, expanding outwards. And as the things were moving, they were starting to lose energy. But it still took about 370,000 years from the Big Bang to the first appearances of hydrogen atoms, where you finally had things cool enough where electrons and protons and even some neutrons could form. And then usually they'd form in one proton and one electron, and we got hydrogen. The simplest, if you look on the periodic table, it's the, number one. So you got all this hydrogen going around, and it's still really hot. So hot, it's glowing. If there was someone with eyeballs that could see it, it would be glowing like the filament of an incandescent light bulb or a neon sign, probably a neon sign. Let's go with a neon sign. So it was glowing to the point that the universe was just awash in light. But over time, it cooled. The incandescence dropped because the temperature dropped. The temperature of the atoms dropped. And so they no longer put off, black body radiation in visible wavelengths where, if something was there with eyes, it would have looked like the universe went dark. No light. Like at our frequencies that our eyes see light, darkness. Just clouds of cooling hydrogen. Maybe a little helium, but mainly just clouds of cooling hydrogen. So this darkness, black universe, lasted somewhere between 200 and 500 million years. So for 200 to 5 million years, the universe was black. And the hydrogen was just flying around. It was still too hot that the speed of it was greater than the force of gravity drawing it together. But somewhere in that 200 to 500 million year time period, enough hydrogen cooled down that it could start clumping up. And more would start clumping up, and more and more and more. So you got these balls of hydrogen that were just pulling together by their gravity. What happens when you get enough gravity, enough hydrogen pulled together? The hydrogen fuses, makes the helium. Little bit of weight difference gets converted into energy. That energy comes out as heat and light. And somewhere, 200 to 500 million years ago, the first star ignited, and the darkness went away. And when it ignited, it produced what's called, a stellar wind, or the stars, when they're putting out this energy, they're also shooting out their outer layers, making a solar wind. So like from our sun, there are, hydrogen and ionized particles streaming out from it just due to the heat and the force of this nuclear fusion going on in the core. And so this one star was sending out shock waves, and they hit other clusters of the hydrogen gas, compressing them, getting them close enough to gravity to pull them together and start fusing. I always think it had to be like in the Lord of the Rings, when they light the beacons of Gondor to send message to Rohan that come, we need you. But somewhere in the universe, this first star ignited, and it triggered the ignition of other stars. And those stars triggered the ignition of other stars, and so on. And so from this one star spreading outwards, light came into the universe. If I had a time machine, people say, where would you go with the time? Oh, I'd see this. I would go back, so far back, to see that happen, to see that first star ignite, and the rest of them ignite from that. I can't imagine anything more incredible. Now, these stars, they were big. They were big clouds of hydrogen, way bigger than our sun. Probably, checking my notes, 8 to 10 times as big as our sun. So really big, a lot of gravity, burning really hot, really fast. So that hydrogen is getting used up really quickly. Because the pressure from the gravity is so much stronger at that core, than in our sun, hydrogen is being forced together more rapidly. So we're getting more energy, so it's puffing it out some. But eventually, all that hydrogen in the sun, or most of it, has been converted to helium. Now, in a star the size of our sun, it's starting with hydrogen, forming helium. Once it gets to helium, the energy output from that hydrogen fusion drops. What happens then is, because you're not putting heat into the systems, the particles start slowing down some. If they're slowing down some, they can be attracted to each other more. And so what you get is helium starting to get smashed against hydrogen. Let's say my head is now helium. So you're getting, hydrogen smashed against helium so much that it's converting into lithium. Or you might get two heliums smashed together to make beryllium. But this can only go so long in a star our size. Once it starts forming helium, the life of the star is pretty much over. It's expanding. It's getting close. All this pressure and the fusion going on, because when if you're jamming two, or a hydrogen and a helium together to make the lithium, the weight difference between the hydrogen and the helium and the lithium is less than the weight difference between the two hydrogens. And so you're getting less energy out of it. So it's not expanding. So you're getting some crushing going on. Long story short, the gravitational force from inside the core of a star the size of our sun basically will only go up to carbon and oxygen. So still, like 6. So if you get like 3 heliums together, it makes carbon. And if you get 4, you get oxygen. But you can't go any bigger than carbon and oxygen, form anything bigger than carbon and oxygen in a sun our size. And eventually, the energy released from that isn't enough to keep it apart, and it just kind of collapses in on itself. Not into a black hole, it just drops down into what's called a white dwarf. So it's a big, super hot, like super, super, super hot clump of carbon and oxygen and helium and hydrogen and lithium and basically everything from hydrogen to oxygen. So at super hot temperature, and basically at the heat of fusion from what was going on. Eventually, these white dwarfs will cool into what's called a black dwarf, where that thermal energy, working like the filament of an incandescent light bulb, is no longer putting out visible light. But the estimate calculations, scientists say the time it will take for that to occur is longer than the universe has been in existence so far. And so all the white dwarfs are from those initial, actually, no, I take that back. Not all the white dwarfs are from the initial first, fires of Gondor, beacons of Gondor igniting the universe. But it's from some of the smaller stars, they're there. But that's if you have something the size of the sun. But if you have what's called a supergiant, and that's a star with, 8 to 10 times as much hydrogen in it at the beginning as our sun. So 8 to 10 times more massive, drawing together. And that's what most of the stars at the beginning of the universe, those first stars that ignited, most of them, they believe, were supergiants. So same sort of thing happens. They start out with just the hydrogen being forced so close together that it forms helium. And then the gravity is so strong that the heliums start fusing together and forming the beryllium and things like that. And you get this things going. And it keeps going. These stars, they're going through their hydrogen fuel really fast. A star the size of our sun, they estimate lifespan somewhere around 10 billion years. And they're estimating right now the sun is about 4.8. So they're figuring our sun is about halfway through its life cycle. Now, in these red giant, or the supergiant stars, they can burn through their hydrogen, even though they have more, way, 8 to 10 times more hydrogen than our sun. But because the gravitational force is so strong and pushing it all together so tightly, that they can go through all their hydrogen in as little as 100,000 years. And if they last 30 to 50 million years, that's bizarre. That is an incredibly old supergiant. So 100,000 years to 30 to 50 million years is the lifespan of the supergiant stars. They have so much mass, that gravitational crushing force is so strong that they don't just stop at oxygen. They start mashing the oxygen and the carbon together and the other things there. And that still produces enough fusion to release energy to keep the star going, to keep it kind of expanded. Eventually, it will go to the point where it's iron. So just iron. It's still, all things considered, one of the lighter elements, only 26 protons. As opposed to uranium. Where is uranium? Yeah, 92. So iron, not a lot going on there. But at iron, that's as far, when you have the gravitational collapse of the biggest stars, the supergiants, iron is the last element that is made by the fusion of the hydrogen and the helium and the carbon and the oxygen and the beryllium and all that. It can't go beyond iron. So where does everything above iron come from? The cobalt, nickel, copper, zinc, molybdenum, tungsten, gold, silver. So eventually the iron, get the temperature there, the iron fusing, the fusion of iron at those gravitational poles can't come together. You can't get the iron close enough to fuse into other elements. At that point, the star is dying out. And so the star, it's losing its energy and it's compacting. And then something cool happens. You actually do, as it cools, get down, and we're still talking millions of degrees. It explodes into a supernova. And in that brief moment of time when the supernova erupts, the pressures are so high that all the other elements form. The gold, the tungsten, the uranium, they are created in the death spasm explosion of a supernova. Earth, because it has so much gold and uranium and so forth, is believed to truly be the basically the intersection of several supernova explosions, because we have so much gold in the universe. And so when you think about it, the silicon, where is the silicon? Okay. Silicon is 14. So, like I said, I'm trying to move my finger here. The biggest atom that our sun can make is oxygen. Silicon is way down over there. So it took supernovas to make the silicon that combined with the oxygen from somewhere else. Maybe the oxygen came from the supernova. Maybe it came from another supernova. But it took the death of these giant massive stars, the particles then, to travel through space and start their gravitational dance until another shockwave came through and forced them together. So I feel kind of goofy here. When people talk about being made of the stuff of stars, they're right. Every bit of us, everything that wasn't hydrogen, and there's a lot of hydrogen in us because water has 2 hydrogen atoms for every oxygen, and we're 80% water. So 80% of us came from the very beginning of the universe. And then everything that isn't hydrogen came from the birth and death of stars. Wow. But there's more. Oh, wow. Okay, we're going to go a bit long. Hope you don't mind. So all this, everything that happened from the Big Bang to the formation of the hydrogen, the particles and how the particles interacted in gravity and speed of light and energy equals mass times and all this sort of stuff happened due to the laws of physics. You might have heard the laws of physics, gravity and all this stuff. Okay. Where did the laws of physics come from? If scientists look at the universe, they basically say there are 19 universal constants. Things that basically can't be broken down, like the gravitational constant, how strong gravity pulls, that stays the same everywhere in the universe. The speed of light, everywhere in the universe. Planck's constant, which relates the photon's energy to its frequency, that's a constant. Higgs field potential, the masses of the fundamental particles. There's all sorts of stuff going out there, but because of the value of these fundamental constants, this universal constants, created the laws of physics, which caused all this to happen. And so one of the questions that scientists have is, okay, why are the laws of physics as they are? Why are these universal constants what they are? There's no answer for that. Well, there's some theories, but why are what they are? And what's really interesting is, so once scientists, figure things out, they like to start poking at it. And in this case, doing calculations and say, okay, what if the gravitational constant was different than what it was? Even just a little, even like, 1% different. Or what if Planck's constant was different, way over here in the 10th decimal place? If any of these universal constants, if you tweak it just a little, what happens? Okay, just to relax you, we can't actually tweak the universal constants in real life, but we can run computer modeling simulations. But what happens if you start tweaking any of these? The universe as we know it can't form. So for that grain of sand to form required, at the Big Bang, these fundamental concepts, the universal constants, to be set at those values for all this to form. There's no reason why they had to be set at those values. They just are. So that's where there's several schools of thought as where did those universal concepts, what decided what those universal constants would be that would result in the creation of the universe. And if you're a person like Stephen Hawking's, the theory is random chance. So that Big Bang, that initial thrust of energy and particles and setting those universal constants was just a random event. And it happened many, 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 many times before, and will happen many, many times in the future. So if you go beyond the universe into whatever is beyond the universe, the thing that caused the Big Bang is happening. And each of these Big Bangs is throwing out different universal constants because it's a different universe. And so if you have an infinite number of universes with an infinite variety of these fundamental concepts, eventually one is going to pop up with the right settings, constants, good choice, to create all this. So could be random chance. Now, you know me, I'm a Catholic, so you know what my sense is. God. Can't prove it. Can't prove Stephen Hawking's theory either. At that point, it's up to you to decide. And whichever, it's good. But to think and random chance, a single grain of sand, all the things that had to occur for that single grain of sand to form. That's impressive. But then think, a living, thinking, sensing, discovering organism. Holy crap. Okay, it's exactly 9 o'clock. Perfect timing. I hope this introduction to the universe gave you an idea of, again, going to use the word miracle of our existence. So at this point, I'm going to run through the sponsors. I know most of you are going to disappear, but we'll see. So, Tina, next week, quantum physics. No, I need a much bigger blackboard. So, okay. So I got to give a special thanks out to, let me bring up the shared thing. So, of course, the Wazoo Survival and the Foraging Bandana, because they're the ones that pay for the StreamYard account I use. We got Uncommon Bees and all their amazing infused honeys, and they got the special coupon going on right now. So check them out. And I'm going to throw these links up after the show here. We have herbs. Tribe member Derek Bible, Ricardo Shilly Shally and his herb shop. And there's a special coupon you can use if you're ordering stuff there. And then, of course, we have Fear and Dread for the survival stuff. Even though we survived, the how many billions of years, it's good to, stick around for a little bit longer. Arbor True. So if you have a tree issue, they will come, they will diagnose the issue. They will do what it takes to either save or safely remove the tree as necessary. And of course, Campcraft Outdoors, maker of all sorts of fine bushcraft stuff. So not your plastic and nylon and fancy neon colors. We're talking old school canvas and wax and steel and things like that, and wool. Do I have everyone? Arbor True? Yeah, and of course, Foraging Texas. Okay. At this point, your star stuff. Multiple stars taking billions and billions of years to create. Some of it, part of you is from the very beginning of the universe. Ooh, here's a good question. Okay. Does a grain of sand have gravity? Yes. If you have a grain of sand sitting out in space, every other object in the universe is pulling on it with the force of gravity, and it is pulling on every other piece of matter in the universe. But like I said at the beginning, the force of gravity drops off exponentially as you move away from a particle. So the overall force of gravity is very light once you get very far away, but that gravity is still there. Other than that, looking at, yeah. Okay. So it looks like no questions. I don't know how many people we had tonight. There's still 35 of you here. But okay, at this point, go forth and shine. You're made of stars. That's what stars do. All right. Good night, everyone.